So far, we've focused on how a desktop is connected to the USF network, but just having a desktop on the network isn't useful unless it's able to communicate with other devices like servers and other clients. After all, the point of networking is to enable communications. So we'll now look at how traffic gets to the internet once it reaches USF's campus core. Looking again at the high-level network diagram, you can see that there are a pair of WAN routers connected to the backbone switches. These devices, WAN 1 and WAN 2, provide wide area connectivity to USF's internet service providers. WAN 1 is a Cisco ASR 9006 and WAN 2 is a Cisco 7600. USF obtains internet connectivity through Cogent, Time Warner Telecom, and Florida Lambda Rail. These links are delivered to USF as Ethernet connections over single-mode fiber. This is the same kind of Ethernet we've used everywhere along the path from our example desktop. Traffic is routed to the WAN routers by the campus backbone, and those routers determine the best ISP to use for reaching the traffic's destination IP. In order to make this decision, the WAN routers run BGP, or Border Gateway Protocol. There are currently approximately 450,000 routes advertised to USF from our ISPs. Once traffic is forwarded to the appropriate ISP, routers in their network and many other networks beyond that ISP deliver the traffic to its destination. When that remote server responds and sends traffic back to the desktop at USF, the same BGP routing tables guide the traffic through the internet back to USF, and our network delivers it back to that machine. We will now look at the network connectivity to the servers USF runs in its data centers. These data centers host all of USF's business data and applications such as student assignments, grades, email, websites, employee payroll, billing, travel, etc. To ensure continuous service, USF maintains multiple copies of its data. USF houses a primary data center on the Tampa campus, a secondary data center in Winter Haven, and a disaster recovery data center at Clemson University in South Carolina. The Tampa data center is directly connected to the campus core as shown in the high-level network diagram. Two Cisco 6500s provide connectivity to all of the servers and devices in that data center. Individual servers within the data center are connected at 1 gigabits per second and 10 gigabits per second speeds. These servers connect to access layer switches which connect to the 6500s. Really, the network gear in the data center isn't that much different than the equipment you see connecting desktops in buildings. For example, all switches providing connectivity to the servers have dual power supplies connected to different electrical circuits. All critical servers have network connections to 2 different switches, so that if a switch failure does happen, the server can send traffic through its other switch. Each switch is uplinked to different Cisco 6500s, so that if one of those 6500s fail, connectivity would continue through the other one. With nearly 10,000 devices making up USF's network, failures are inevitable. So the network engineering group runs software to monitor every one of these devices. We check their availability and health every 3 minutes. We check things like CPU, memory utilization, optical power levels on the fiber links, room temperatures, UPS capacity, and general functionality of the device. If any of these parameters are out of normal values, we are notified and someone from the operations or engineering group will troubleshoot the issue. We also monitor various statistics from our network gear. We graph input and output traffic levels for every switch port and router port, concurrent users and throughput on every wireless access point, network performance statistics across our backbone and inter-campus WAN links, and call volumes on our telephony systems. Basically, we monitor as much information as we possibly can and attend to any unusual observations. These statistics help us with capacity planning, troubleshooting, and even security. For networks the size of USF's to function, the equipment used in them must be reliable, secure, feature-rich, remotely manageable, and have an assurance of technical support from the manufacturer. It must be what's referred to in the industry as enterprise-class gear. Equipment from vendors like Linksys, D-Link, and Belkin is typically SOHO class, small office or home office class gear. These low-end devices work well in the home or in a small office that's not part of a larger enterprise network. They have many useful features that work in that environment. For example, they are inexpensive and usually require no configuration and are ready to run out of the box. When they fail, they just need to be replaced with similar equipment. For an office with 5 to 10 users, this is adequate, but they do not do well in a large network like we have here at USF. USF needs many high-end features not available in SOHO class gear, and we need the ability to remotely monitor and manage all aspects of each network device. Enterprise class equipment is certainly more expensive than SOHO gear, but that extra cost helps guarantee the networks we build provide the level of service our users demand. They are capable of handling heavy traffic loads from thousands of users. Their remote administration and configuration features allow a small group of network experts to manage thousands of devices. Their configurability allows USF to respond to changes in network needs by reconfiguring traffic routes as appropriate. The entire USF network of nearly 10,000 devices is managed and operated by a small group of experts. 5 engineers design and support all of the networks and services. 4 network operations staff handle tasks such as equipment configuration and installation. We also have several staff maintaining the physical cabling, handling requests from users for adds, moves, and changes, and we have a team who handles telephony for the campus. You have seen USF's network from the desktop all the way up to the campus core and out to the internet. You've seen how traffic gets to the internet and how the infrastructure in USF's primary data center is designed. We've discussed how all of this infrastructure is monitored and what kinds of network gear are required for an enterprise-class network. I could literally spend hours talking about any one of the topics we've covered in this video, but hopefully this short introduction has provided you a good understanding of the technologies which make up USF's network. The network of any large enterprise will share many of the similarities with this network. And if you find these technologies as interesting as I do, I hope this has encouraged you to continue learning about them and perhaps even consider working on them.